Hello everyone, I'm Truman. Today our group will do the introduction of paper, a reference architecture of plausible strata image projection within 3D X-ray computed tomography volumes. At the beginning, let me do the brief introduction of the paper. In our daily life, we need to carry out a security inspection when taking subway, train, plane, and other means of transportation. However, the benign X-ray used for security inspection can only determine the general outline of the item in the baggage, but cannot accurately give the real picture of the items and the accurate position in the baggage, as shown in the left figure followed. The application of the TIP, thread image projection technology to benign X-ray security inspection, superimposing some features on such fusing image, as shown in the right figure followed, so that security inspectors can more accurately identify and determine the category of the item in luggage, improve the working efficiency, and ensure our travel safety. The paper discussed the reliable approach of adopting 3D TIP technology in 3D CT images of the luggage. Based on particle swarm optimization PSO algorithm to generate the mental artifact at the auxiliary to determine the position of the objects, which will be inserted features. The paper also provides a useful tool for us to implement PSO, and the tool, which is called Python Swarms, is an intensive research toolkit for PSO in Python. In the code part, we will show how to install the toolkit and use the example of optimizing a thread function, and is find the minimal as the code part of our presentation. And before we beginning the code part, we should know what is PSO. So then we can comprehend the followed code easier. Assume that a group of the treasure hunters are looking for treasure. The treasure is mental. Hunters carry mental detectors and walkie-talkies, but the mental detectors can only find the approximate location of the treasure, but they don't know the specific location. Hunters can share their location and their approximate distance from the treasure through walkie-talkies. Everyone is looking for the treasure at different speeds, and their location information is constantly updated because they can share information through walkie-talkie, and other treasure hunters will keep approaching the treasure hunters close to the treasure. In this way, the efficiency of finding the treasure will be greatly improved. PSO is such an algorithm to optimize a group search. Therefore, we treat each treasure hunter as a particle, and this particle has only two properties. One is position, and the other is speed. Speed represents the speed of the movement, and position represents the direction of the movement. Each particle separately research for the optimal solution in the research space, records it as the current individual extremely value, shares the individual extreme value with other particles in the whole particle swarm, and find the optimal individual extreme value as the current global optimal solution of the whole particle swarm. All particles in the particle swarm adjust their speeds and position according to the current individual extreme value found by themselves and the current global optimal solution shared by a whole particle swarm. So this is the basic idea of PSO. So let me welcome our partner to do the code part. Okay.
Hello, I'm Ethan, and me and Steve will do the code part. So first, let us show you how to install the toolkit. So in the example of optimizing a sphere function and the minima of the sphere function fx equals to x squared, we first need to import the toolkit, which we import Python swarms as PS in the first line. Then from the toolkit, we need to import an object, which is a sphere function we need to use later. So we import the function as fx next set up the parameter, which are parameters that are artificially set before starting machine learning. So here we can call them PSO parameter, and C1, C2 are acceleration constant, and W is inertial weight. The specific meaning of these parameters, you can find them from Wiki or Baidu Encyclopedia interest from about PSO. Then in the sixth line, you can see we set the number of particles as 10 and the dimension as 2 since we optimize a 2D function, and we use the hyperparameter we just said before as the option in this instance. The end line is to perform optimization, and we can get the particle with best cost and the best position with 100 iterations. Of course, this is not the real best solution since we only iterate 100 times. As the times of iterations increase, the answer we get will be closer to real optimal solution. But 100 times are enough for finding a approximate optimal solution. You can see our goal is to find the minima of sphere function fx equal to x squared, and we know the global minima is at 0 point. So you can see the best position we got is very close to 0.
Hi, I'm Steve. Next is for the hyperparameters. We can also use the hyperparameters search tools supplied by this Python swarms toolkit to find out. Next, we will show the successful running in our computers. If you observe the figure, here we still use the sphere function as our object, and after we run in this code, we can begin to type best score to get the integer weight W, and type the best option C1 or C2 to get the acceleration constant C1 and C2. And these three parameters are the hyperparameters we need to use in the last code to optimize the sphere function, and they are stored in the option library. Next, let's do swarm visualization, which can show us the running process of this PSO algorithm. This is the cost history diagram, and you can see the cost value is gradually approaching to 0, which means it's closer and closer to the option solution. The next is animation in 2D and 3D to find the minima of the sphere function. In 2D animation, here is the code, and this is the diagram. This is the picture, and this is the 3D animation code, and here is the picture, the result. Okay.
So now let me to show how the code works successfully in our computers. So first we need to install the toolkit, which is the Python swarms. So you can see this is successfully installed the py swarms, and the version is 1.30. And we need to open IPython to enter our code. So first download the IPython tool. You can ignore the warning. Wait till the download. Okay, successfully download the IPython. Okay, there is some small problems. This is because why we cannot open the IPython, because we don't configure the path of the of the Python script. So you can see when we add the scripts path to the environment, we can successfully open IPython here, IPython here. Okay, we can continue to our code part. Let me check the code first. So in the IPython, we need to enter our code. First, we want to optimize the sphere function. So just copy and paste the code and enter the code. You can get the solution. So you can see there is a solution, the best cost and the best position, which my partner mentioned in the code part. So go to the next part. The next part is to use the hyperparameter search tools. You can see there is C1, C2, and W, which are all the hyperparameters. But the hyperparameters we cannot know if we cannot know easily. So we can use the hyper search tools to search for the 3 parameters. So enter the code which showing on the GitHub and run the code. So after running the code, we can just type best score, which is which we can get the W is 2.7 and so on. And if we want to get the C1, we can type best options. C1, and this is C1 value, which is 2.05. Also, we can get C2. Which is 8.8. Okay, go to the next part. is the swarm visualization. If we want to know the code history, we can type the code given by the GitHub. So you can see when we run the code, this is automatically show us the figure, which will show the cost history. And the meaning of the cost history, my partner also have explained in the last part. So go to the next part. I will show you the 2D and 3D visualization of the code. After we finish the environment configuration, we can just run the code by this code. So you can see the 2D diagram, 2D animation. You can see these particles are trying to find the optimal solutions, which is the minimum of the sphere functions, so fx equal to x squared. So you can see every particles will share their positions and speed. So the other particles will try to close to the particle which have the best solution currently. So next is the 3D animation. So you can see this is a 3D animation. In the sphere functions, this is the same meaning with the 2D animation. These particles are trying to close to the best solutions, which is 0 point. Okay, that's all of the code showing, and you can see the code. All of the code are successfully running on our computers. The next part will introduce the conclusion part.
Hello everyone, my name is Wang, and I will introduce the relationship between the PSO and the paper. Now we have a basic idea of the PSO, and we roughly know how to use the Python swarms toolkit to do PSO. Then what is the relationship between the paper and the PSO? Now we can conclude that PSO is used to find the optimal solutions that meet the conditions. And we talked about generating reasonable metal artifacture based on PSO in the first section. Since the paper used the CT volumes as the example, so we first need to learn about the voxel. It is very simple to compare the voxel if we know what is a pixel. If we say pixel are the invisible units or elements in the 2D image, then the voxel are the invisible units or elements in the 3D image, just like this picture. And and so after knowing what is a voxel, let us return back to the paper. With the segmented 3D object and the projection cost map of a bag volume, the insertion is boiled down to optimization problem, which aims to find the optimal insertion location and threaten object orientation. That is, we want to find where to generate the metal artifacts, which can be considered as an insertion problem. So that means we need to find the optimal solutions, which are the position of voxel. And PSO is just an algorithm used to find the optimal solution under unknown conditions. Thus, so through a series of mathematics formulas to calculate the required conditions, which should be included in the PSO as parameters, then can finally get some images with superimposed features. For instance, metal artifacts. The paper also evaluates the experimental results, and through qualitative and quantitative evaluations, the team got the conclusion that their TIP approach is able to generate realistic and plausible 3D baggage CT volumes containing fictional threatened signatures, which can be widely used for training baggage screening operators or automatic threat detection models extending off. Finally, the conclusion is this article discusses the use of TIP technology to generate fixtures threatened fixture for CT images, which are used to help security personnel better identify the potential threatened items in the luggage and package. Where these threatened features are to be inserted, they need to find a reasonable optimal solution through PSO algorithm, which use the research to tricky the pattern swarms. Finally, they came to the conclusion that the method they proposed was feasible. That's all. Thank you for your listening.